there, my name is Keke. Welcome to the 5th lesson in our series on transverse pulses and waves. In this lesson, we will investigate what happens when two pulses meet in the same medium. Now, I'm sure you have seen all kinds of things being mixed, like milk, eggs, and flour are mixed together to form a batter. When this is cooked, we get flapjacks. Cement, sand, stone, and water are mixed together to make concrete. We know that when one mixes some things together, the result of the mixing can make something new and better. But of course, not all things are able to mix together. Look at these billiard balls. When they move towards each other, they do not mix, but a collision takes place and both the balls bounce off each other. So what happens when two pulses move towards each other in the same medium? Do they mix in the collision or do they bounce off each other? Well, fortunately, there is a rule to help us explain what happens. This is called the principle of superposition. By the end of this lesson, you should be able to predict and explain what happens when two pulses meet by applying the principle of superposition. Now, you may be wondering when two pulses are likely to meet and mix. Have a look at this situation. This slinky spring has been fixed at one end. When the free end is moved up and down quickly, a half pulse moves through the slinky. Notice the crest of the pulse lies above the rest position. At the fixed end, the crest is reflected. Can you recall what type of reflection will take place here? That's right, the reflected pulse is inverted at a fixed end. Now, if the free end is moved up and down again, at the moment of reflection, a second identical half pulse will start to move towards the reflected pulse. Before we observe what happens when these pulses meet, you might want to make a prediction. Do you think the pulse will be reflected when they meet, or do you think they'll mix together? Let's have a look at what happens. So, was your prediction correct? Now, let's break this motion down into a series of photos to analyze what's happening. In this first photo, you can see the second pulse is above the rest position. The reflected pulse is below the rest position. But remember that the particles of the spring are moving perpendicular to this motion. The particles of the second pulse experience an upward force and move up. The particles of the reflected pulse experience a downward force and move down. Notice the maximum displacement or amplitudes of these two pulses are identical in magnitude but opposite in direction. Now, what do you think will happen when the pulses move into the same part of the medium? Think about the forces acting on the particles. This photo shows what happens when the pulses overlap in the same region of the medium. It looks like the medium has not been disturbed. This is because the forces experienced by both pulses are equal but in opposite directions. The particles where the pulses meet are being pulled upwards by the second pulse and downwards by the reflected pulse. The overall or resultant force on each of these particles is then zero. When pulses meet or mix, it's called interference. The pulses have interfered with each other. When pulses that are on opposite sides of the rest position meet, we call this destructive interference. Now, it's very important to notice that even though there did not appear to be any pulse present in the second photo, they are in fact present. You could draw the pulses in on the photo. The interference of these pulses doesn't destroy them totally. Look at our next photo taken right after the destructive interference took place. The pulses are both now in different parts of the spring. The second pulse is still moving above the rest position in its original direction, and the reflected pulse is moving in its original direction. Now, this mixing is different from the mixing we were talking about earlier. In fact, interference is an identifying property for pulses and waves. Now, can you imagine what would happen if two billiard balls interfered destructively with each other during a collision? When billiard balls collide with one another, we would have no billiard balls for a moment. But then they would reappear and continue to move just as they were moving before. But this doesn't happen. Only pulses and waves can experience interference. Particles like billiard balls clearly do not behave like pulses and waves. So far, we have observed destructive interference that takes place between two identical half pulses. The reflected pulse was inverted because the end was fixed. Now, let's repeat this investigation with both ends of the slinky free. Do you remember what happens to a pulse that is reflected from a free end? Watch this. Look, the crest travels towards the free end and is reflected but not inverted. The reflected crest is above the rest position. Now, a second pulse is generated at the moment of reflection. This crest also lies above the rest position. I think you could easily predict that these two crests will meet. But can you predict what will happen? Watch carefully as the two crests approach each other. I have once again taken some photos of this motion to analyze. In this first photo, the crests are moving towards each other. Here the particles in both crests experience a force that causes them to be displaced upwards above the rest position. Now, in the second photo, we will see what happens when these crests move into the same part of the medium. Here the particles have been pulled upwards by both pulses to form a pulse with much bigger amplitude. These pulses have also interfered with each other, but clearly this time the effect is different. Here the pulses are both on the same side of the rest position. We call this type of interference constructive interference. So if two troughs were to meet, you would also get constructive interference, and you would see a bigger trough. At the start of this lesson, I told you we would establish a rule called the principle of superposition to predict and explain the special behavior of pulses and waves. Let's have a look at this principle now. The principle of superposition states that when two waves interfere, the resulting displacement of the medium at any point is the sum of the displacement of the individual waves at the same point. I know, that's quite a mouthful, but I think you'll understand it better if you apply it to a practical example. In this example, we have two troughs moving towards each other. Both the troughs have an amplitude of -2 centimeters. Can you predict the amplitude of the trough formed when these pulses interfere constructively? Remember, the amplitude of a pulse is the maximum displacement from the rest position. So we want to apply the principle of superposition where the displacement is maximum. Have a closer look at the statement again. Look, this says the resulting displacement of the medium at any point. So in our example, we want to find the resultant displacement at the point it is a maximum to find the amplitude of the new pulse. The amplitude is equal to the sum of the displacements of the individual waves at the same point. Well, this means we must add the amplitudes of the original pulses together. So in our example, both the troughs had an amplitude of -2 centimeters. This means that the amplitude of the pulse formed by constructive interference will be -4 centimeters. I hope you can see that it's quite easy to apply the principle of superposition. In this example, we look at the point where the two troughs overlapped to form a new maximum displacement. But the principle of superposition can be applied to any point where two pulses or waves overlap. Have a look at this animation to see how the principle of superposition is applied to two waves. Wave 1 meets up with wave 2. To get the resultant wave 3, we must add the displacements of the particles in wave 1 to those of wave 2 at each point that they overlap. Look at point P on the wave. This displacement was found by adding the displacement RS and QS together. This is an example of constructive interference. The new wave has a greater amplitude at this point than either the original waves. What about point C on the new wave? Look carefully. Here the displacement on wave 3 is positive AB. The displacement on wave 2 is the negative value BD. When these are added together, the result is negative BC. This is another example of destructive interference. At this point, the original pulses were on the opposite sides of the rest position, but did not cancel each other out completely. The resultant wave is smaller than one of the original waves at this point. Now it's time to apply what we have learned today. Look at these two waves. Wave X has an amplitude of 4 centimeters and a wavelength of 10 centimeters. Half a wavelength is shown on this diagram. Wave Y has an amplitude of 2 centimeters and a wavelength of 5 centimeters. One wavelength is shown on this diagram. Now, for your task today, I want you to apply the principle of superposition to these waves. Sketch the resultant wave formed when wave X and Y interfere with each other. I suggest that you draw the waves X and Y on the same section of paper. You may find it easier to use squared or graph paper. Then use the principle of superposition in at least 8 points to get the shape of the new wave. In our next lesson, we will look at what happens when waves continually interfere with each other in a medium. See you then.
Yeah.